Day 161, Physics, Photoelectric Effect. One of the main ideas in the photoelectric effect is this is really a conservation of energy problem. We are going to have photons with energy that are going to transfer their energy to electrons. So let's talk about that. We've calculated the energy of a photon in the last lesson. The energy of a photon is E equals hf. But this was a famous experiment or famous phenomenon. Really, it was discovered or developed by Albert Einstein. This is what he won his Nobel Prize in physics for, is the photoelectric effect. He did not win his Nobel Prize in his studies for the theory of relativity, which he's more famous for, the E equals mc squared. But photoelectric effect, which is support for the photonic nature of light. Light acts like a particle. So what, may you ask, is the photoelectric effect? Well, it's something to do with photo or photons or photographs or visuals, and something about electricity. Now, electricity is typically the movement of electric charge, typically electrons. In this case, it's electrons that are moving off of a metal surface. But the basic definition is the photoelectric effect is the ejection or emission of electrons from metal surfaces when struck by high energy photons. Is support for the particle nature of light. The photonic nature of light. All right, so there's some terms here that are all very related and you can get a little confused, so let's practice these. You have what are called photosensitive metals. So the photoelectric effect has to do with photons hitting metal surfaces. And down here in this picture, bottom left, this black rectangle represents a metal. It could be aluminum, copper, gold, silver, and there are some differences you'll see in a table here in a little bit. But these little circles with dashes in them are electrons. Obviously that metal is full of atoms that have protons and a nucleus, but this just represents loose electrons. Over here on the left are photons, and they're purple in my case here, which are high energy photons. So the photoelectric effect is most effective when you have high energy photons. Low energy photons don't really do well with the photoelectric effect, as we'll talk about. Anyways, we have what happens here is photons, which are flying around in any given room, light, hit this metal surface or a metal, and they get absorbed by the electrons, in a sense, and they jump off the surface. So these two electrons here were released. They call them photoelectrons. It says that in the problem here. Oops. Photoelectrons are electrons ejected or emitted. So we have that here in this case. These two electrons came off that surface because some photons hit them and gave them energy to then escape that metal. It's a transfer of energy from the photon to the electron. Now, on the right picture here, and actually we can make a little correction here. Well, it's not really correction. The energy of a photon, this is E equals hf. This is F here. Let me switch to red so you can see this better. Some books have this mu, this V shape. Let me go back to draw. Red. Okay. So in this equation here, I'll circle it. Change that to an F. E equals hf. That's the energy of a photon. We did that yesterday. H is Planck's constant. So energy of a photon is h times its frequency. So this is representing this little gray thing here at the bottom. Represents, in this case, potassium, a metal. And this red is a photon coming in, hitting that surface. And because the red photon, which is a large wavelength but low energy, right? It's, say, a red photon has 1.77 electron volts of energy, and some have a little bit more than that, depending on the shade of red, but around 1.77. This one has 1.77 electron volts of energy, hits that surface, and gets absorbed, maybe turned into heat, but it does not photoemit an electron, because this photon's not strong enough. You need strong photons. It's not the number of photons, it's the energy of an individual photon that's responsible for the photoelectric effect. That's the most important thing to remember about the photoelectric effect. It's by individual photons, a transfer of energy by an individual photon, not a large group of photons. For example here, this green photon, which comes in with an energy of 2.25 electron volts, is enough to get an electron to photoemit. The energy is not all that energy is transferred to the electron, which we'll talk about, but at least some of it. In fact, if you look at the bottom here, it's kind of hard to see, but this is potassium. It says it needs 2.0 electron volts of energy to get the electron loose. We'll talk about that in a minute. That's called the work function. That's the energy just to get the electron loose from the surface. If you have a photon with more than that energy, for example, in this case, this green photon here in the middle has an energy of 2.25 electron volts, which is a little bit bigger than 2.0. In fact, if you subtract those two numbers, you have an excess of 0.25 electron volts. And that energy, transfer of energy, actually goes to the kinetic energy, 1/2 mv squared, for the electron. And then you could calculate the velocity, the maximum velocity, using Ke equals 1/2 mv squared. When we do that in these problems, the mass will always be the mass of the electron, 9.11 times 10 to the negative 31st kilograms. And then just plug in 1/2 mv squared. You have the energy, 0.25 electron volts, which you would want to convert to joules, as we will do. You can get the velocity of the electrons as they come off that surface. So if you have an even higher energy photon, like this blue or violet one, shorter wavelength but higher energy, 3.1 electron volts, that exceeds the 2.0. It's very simple subtraction. You have an excess of 1.1 electron volts of energy, convert to joules, but let's just say it's 1.1 electron volts of excess energy that goes to the kinetic energy of this electron. That's more kinetic energy, which means this electron here, this photoelectron here, has a bigger speed because it has more energy than this one over here from the green photon. And the red photons can never, in this case, cause the photoelectric effect. They cannot emit photoelectrons because they're below the threshold or the work function, the 2.0. Red will never be able to do that. And for example, you could have a really bright beam of red light. And a bright beam of light refers to the number of photons, not the individual photons, but the number of photons. So you could have a very, very bright, like say a red laser, with those particular photons in there. And that beam can be so bright and so energetic because you have lots of photons. They could burn through the potassium. They can burn through the potassium, make a hole in the potassium, but they will never cause photoemission because no individual single photon is strong enough to get the electrons to come off, because it's a one-to-one phenomenon. That's one thing to keep remembering here, and I'll remind you of that. So if we go down here, I've talked about the threshold frequency. The threshold frequency is the minimum frequency at which electrons are emitted. And once again, actually, these four things are really all the same thing. I'll put that in parentheses. They're not exactly the same. They're just different references for the same thing that will connect together, as you'll see when we start doing the problems. But for example, if photons come in that just have the threshold for the potassium that we just did, the threshold was 2.0. That's what it takes to get this going. You need photons of 2.0 or more. Actually, 2.0 is the break even. That's why we call it the threshold. Well, a photon that has that energy, we can do E equals HF to get its frequency. Also, what we did yesterday, or the day before, is if you know the frequency of that photon, you can use V equals lambda F to get the wavelength. So the threshold frequency, the threshold wavelength kind of go together, and they all are associated with an energy, and that energy is called the work function. So all four of those things are connected together. They go together when we calculate these things, and you'll see that here in a few minutes. So we'll practice that. But we will be coming back to E equals HF over here and V equals lambda F. Those are two equations that we'll be using a lot, in addition to our new, I'll circle those, equation, which is the photoelectric effect equation, which is down here on the left. There's our new equation. It's really just a statement of conservation of energy. We have this E over here on the left stands for energy of the incoming photons. That's energy. Energy of a photon striking a metal surface. This is indicative or unique to each particular metal surface. I have a table here over on the right which tells you what the values are for different metals. But that's energy. For potassium, we know it's 2.0. Actually, it's saying something different. In this table, it says K is potassium, right? It's 2.3, so I guess there's a little discrepancy here. But 2.3 in this table, 2.0 up here at this top problem. But you just use what they give you, and I would give you credit for either one of those. And this is also energy, kinetic energy. So what's going to happen is you have incoming, energy of a photon. Say it's got 5 electron volts, and this is 2, so the kinetic energy would be 3 electron volts. It's pretty simple math. Sounds simple. What makes these problems somewhat challenging is that some of these problems have 5 or 6 steps. When you put 5 or 6 simple steps together, it's not a simple process altogether, so we're going to practice that. So for example here, what is the largest wavelength of light that will eject electrons from a barium surface? Whenever it says largest wavelength or minimum frequency, because the largest wavelength are lower energy photons. So what's the lowest energy photon that can eject electrons from barium? Whenever it says this, largest or smallest, typically what that means is we have electrons that are just meeting, or the photons that are just meeting the work function. So you look up barium over here. Barium, Ba is 2.5. So the work function for barium is 2.5. In other words, what we're talking about right now is we want, if you look at that equation above there, we have E equals, I'll write it down. And I usually don't write the subscripts. E equals work function. It's always assumed those same subscripts. Plus kinetic energy. The kinetic energy is always the kinetic energy of the electrons. But what they're talking about here in this particular problem is that this is 0. In other words, what energy photons do we need to just hit the threshold for barium? Well, we need photons that have an energy of 2.5. So we need E equals, well, HF is the energy of a photon. We need photons that have 2.5 electron volts of energy equals, and then we need to, because we're in electron volts, we need to use 4.14 times 10 to the negative 15th. That's a 15 there, times F. It's 4.14 times 10 to the negative 15th times F. So you do the calculation there, and you get the frequency of those photons, I believe, is 6.04 times 10 to the 14th. 6.04 times 10 to the 14th hertz. That's the frequency of those. I'll fix this up here. This was supposed to be 10 to the negative 15th. There we go. So that's the minimum frequency, but the minimum frequency is the minimum energy, 2.5 electron volts, but that matches the largest wavelengths. But we got to get the wavelength. Well, to get the wavelength, we have to do V equals lambda F. So I'll just do that, V equals lambda F for those photons. We need photons that have that frequency. Photons always have a speed of 3.00 times 10 to the 8th. We're looking for a wavelength that matches that frequency, 6.04 times 10 to the 14th. So that wavelength, hopefully this is not off the page, is 497 nanometers. 4.97 times 10 to the negative 7th is 497 times 10 to 497 times 10 to the negative 9th. So, and if you look in tables, there's a table on the next page. That wavelength is associated with orange light. You don't need to write that down. You would need a table to see that. So orange light would be the first color light that would then cause photoemission from barium. Anything beyond orange, yellow, green, indigo, blue, indigo, violet, would all then have excess energy to give the photoemitted electrons even more energy. I have a little simulation here. Hopefully I can find it. Yeah, here it is. So what we have here in this middle part, this part right here represents photons coming in, hitting a metal surface. And these blue dots represent electrons being emitted, photoelectrons. Okay, so, and there's also some other things here that you don't need to worry about right now, but basically we're just looking over here where the photons are coming in, hitting a surface, and actually what happens is they come over here, and that's a positive surface. I think it's what, a cation. yeah, doesn't really matter. Well, it's positive. And then there's a circuit that brings the electrons back around. But we're looking mainly over here, the sodium. And if I increase, I have a slider up here at the top. Right now I'm hitting this sodium way up here on the left with a 475 nanometer wavelength, which is in the, I guess, green-blue area of the spectrum if you look at a table or do the calculations. But if I go to a higher energy photon, like if I go back over here and make it like blue or violet, now what's happening is the electrons have more energy than before. They have more kinetic energy because the blue photons always work better than green. Green always works better than yellow. Yellow always works better than orange, and gives them more energy because they have more incoming energy and they have excess energy to give to the kinetic energy of the photons. The photoelectrons, the emitted electrons. If I go way over here to red, okay, so red photons are doing nothing. Red photons are doing nothing here. They can't photoemit. So if I then do something halfway in between, well, if I go, okay, so that's close to the threshold, because what I'm noticing here is they don't have a whole lot of speed. If I go to an even lower energy photon, if I go to something even lower green, I'm real close to the threshold. If I keep sliding, I'm sliding that gray slider at the top there, and I'm getting closer and closer to the threshold because the electrons have less and less speed. And if I keep going a little bit more, eventually, I think it's like 540, 42, 44. Okay, at 548, I think it's at 545 or 546, that's the threshold, the wavelength. And you could figure out what frequency that is. If I went in there, I think if I type in 545, I think 545 actually is the threshold. Doesn't really matter. 45, hit enter. I think 545, yeah, 545 works. And if you try 546, I'm not going to do it right now. Well, I can try it. 545 or 546, if I go back one here, go to 546, higher wavelength, lower frequency, less energy, it stops. So you could say the threshold's either 545 or 546 nanometers. That's the threshold wavelength. You can calculate the frequency associated with that. And once you're below the threshold, nothing comes off. If you're above the threshold, they will come off. And the higher you are above the threshold, like if I go back up above the threshold, you're going to have a lot of high-speed electrons. Now, if I also then, I can decrease the intensity. In other words, if I slow down, or not slow down, if I decrease the frequency, in other words, dim, that's a dimmer light hitting this, there's just fewer electrons. All these electrons still have the same speed they had before. Maybe it doesn't look like that, but there's just fewer of them. So the intensity is what determines how many come off. The frequency or the energy of each individual photon determines whether they come off or not. So for example, I can slide this back down to red. So this is a low intensity, be a dim red. Well, red doesn't work no matter whether you're dim or bright. I can increase the brightness of the red. I'm going to slide up and get a lot of red coming in. There's a whole bunch of red photons coming in. I'll decrease. So there's a bunch of red photons coming in, a whole bunch of them, but it's really, really bright. Could burn a hole in there, but it's not going to emit the photoelectrons because it's the individual photons that cause photoemission. So that's photoelectric effect. Let's do one more sample problem here. Let's go back to this. Okay, so I'm hoping, yeah. Actually, I got to go back to the next page. Here we go. The threshold for a certain surface is 284. What metal might this be? So once again, if you're looking at the equation, E equals, let me fix that. Energy of the incoming photon equals the work function plus the kinetic energy if there's excess energy. But they're talking about threshold. Whenever we're talking about threshold, which they usually start off that way, or sometimes that's the end question, this is zero. There's no kinetic energy. So the energy of the incoming photons now matches the work function. So we have something that has a wavelength of 284 nanometers. Well, I need to use V equals lambda F and then E equals HF. Those are the three equations you're going to be using. The photoelectric effect equation over here on the left, then the standard V equals lambda F and E equals HF. Sometimes you do it in different orders, but in this case, we're going to start with V equals lambda F, because they gave me lambda here, the wavelength, and I know the speed of these particular photons. The speed of a photon is always 3.00 times 10 to the 8th equals 284 nano. Nano's negative 9th. I'm just putting the n in there to remind me of that, and the times F. So F is the frequency, n is 10 to the negative 9th. So if I do the math there, that comes out to be the frequency of these photons, at this case for the threshold, is 1.06 times 10 to the 15th hertz. These are the threshold photons. But I want the, that's the frequency of those photons. I want the energy of those photons so that I can look up in the table to see what metal this is. So I'm going to take that and go over here. So the energy of those photons is, and I want to do it in electron volts because that's what the tables are in. So 4.14, you could do it in joules and then convert. 4.14 times 10 to the negative 15th times that number, 1.06 times 10 to the positive 15th. I'm off the page here. Okay, but that's 1.06 times 10 to the 15th. So the energy, so I just plugged that number in, and you get 4.37 electron volts. That's the energy of the threshold photons for this particular metal. Then you go back and look in the table, and hopefully you have something that matches up there. And you don't, but you got to find something that's close. Well, the closest you can come to is these two right here, the aluminum and copper. And the 4.37 is almost halfway between. I would give you credit for either one of those. The threshold, so the threshold here was 4.37, the work function. I'd be conservative, I'd say aluminum. And if you said copper, I would take it. So that's the particular metal we're dealing with here, aluminum. That's based on the table. All right, part B, then calculate the wavelength of light required to produce photoelectrons that now have a speed of 6.0. So now we're resetting the problem. That was part A. That was all part A. Part B, then we're going to start over. E equals, okay, a little better here. E equals the work function plus the kinetic energy. So now the kinetic energy of the electrons is not zero. The only thing that stays the same between part A and part B is the work function. We still have the same metal. So the work function is still 4.37 electron volts. We have now photons with more energy. And so we're going to have emitted electrons that have more kinetic energy. They're going to have a higher speed. So I can calculate, let me change my color here. Try this. All right, the kinetic energy of my electrons, because it gives me the velocity of these electrons. So kinetic energy is 1/2 mv squared. That's another equation you need to know. I could put that up here at the top, but most of us can probably remember that. Ke equals 1/2 mv squared. And in these problems, it's always an electron. The mass is always, well, going to be given 9.11 times 10 to the negative 31st times the velocity of these electrons, 6 times 10 to the 5th squared. So the kinetic energy of these electrons, we plug that all in, is 1.64 times 10 to the negative 19th joules. Now, in this problem, I have my work function. I'm looking for, okay, I'm going to go back over here to the left. So I have E equals, I've got my work function, we still have aluminum. We have 4.37 electron volts for my work function. Plus, but I don't want to put in mismatched units. I either got to convert the 4.37 to joules or the 1.64 that I just calculated to electron volts, which that's what I'm going to do. I'm going to keep these in electron volts. So it's your choice, but in this case, I got to convert. I'm going to convert the 1.64 times 10 to the negative 19th joules. And the conversion factor, if you look it up, is that, let's see, it's 1 electron volt is 1.60 times 10 to the negative 19th joules. That's the conversion. So if you do the math there, you end up with the kinetic energy is 1.02 electron volts. All right, so I'm going to take that and bring it back over there to the left. So that's 1.02. So the energy of the photons I now have, they're beyond the threshold. The threshold in part A was 4.37 electron volts for those photons. Now I have 5.39 electron volts for these particular photons. That's electron volts. These were all in electron volts. So I got to figure out the wavelength or frequency. I can do either when I go back. I need the wavelength. So, but usually I calculate frequency first, and you might be able to take some shortcuts by now. But so I have 5.3. Well, I'll show you what I'm plugging into. I'm plugging into E equals HF. I know E of these photons, the energy is 5.39 electron volts. So I have to plug in the 4.1, I have to keep it in electron volts, 4.14 times 10 to the negative 15th times F. So the frequency of these photons is 1.30 times 10 to the 15th hertz. All right, but I need the wavelength. Okay, I'm going to erase a few things here, so hopefully you have this all written down or pause it. I'm going to erase all this over here so I can work. I'm out of space. So, all right, the energy of these, well, I have the frequency, I want the wavelength. So we go back, I do V equals lambda F. Once again, the velocity of photons is 3 times 10 to the 8th. The velocity of electrons is never 3.0 times 10 to the 8th. They are, well, in this problem it was whatever it was, what was it, 6 point, I forget what it was. I just erased that. Well, it's written now. 6 times 10 to the 5th meters per second. Anyways, photons are 3.00 times 10 to the 8th equals the wavelength we're looking for times that frequency we just found, 1.30. That's 1.30 times 10 to the 15th. And you calculate the wavelength. It comes out to be 231 nanometers. 231 nanometers. That's my answer. 2.31 times 10 to the negative 9th. It's 2.31 times 10 to the negative 7th. 231 times 10 to the negative 9th. That's the wavelength. That turns out to be in the ultraviolet range. So these are way beyond visible. These are really high energy photons. Doesn't really matter. You have to look that up in a table. But some other thoughts about photoelectric effect. Okay, once again, it's not how bright the light is. It's how high the energy of each individual photon is. It's a transfer of energy from the photon, first of all, just to get the electrons off. That's a work function. And excess energy goes to the kinetic energy of the photons, conservation of energy. So even if you have photons that are below the threshold, no matter how bright they are, how many there are, they'll never get the electrons to emit. This is a practical phenomenon. They're used in light detectors like your camera flash. How does your camera flash know to turn on when it's dark out? Well, because it has a sensor that's either sensing when it's light out, it's sensing that there is a photoelectric effect going on because there's photons in any given beam of light. There's always some high energy photons. And then it doesn't turn the flash on, but when it gets dark off, it senses that there is no photons, so it turns the flash on. Same thing for things that turn on at night, lights that turn on at night. Motion sensing a little bit different, but light sensing that just turn on because it gets dark is because of the photoelectric effect. Motion sensing is a little bit different. So there's a practical application. Photoelectric effect, the emission of electrons from high energy photons, conservation of energy.